Thank you so much. And thanks so much to everyone for coming. It's so crowded that literally my mentor is blocked outside. All right, so here you see on the screen there are two representations of the same brain network, which is typically made up of hundreds of nodes, which represent the brain regions, and tens of thousands of edges representing the connectivity among the nodes. And one could study this brain network on multiple scales. So first, on the finest scale, for example, or the micro scale, we could study these individual nodes, we could study these individual edges, rather. And importantly also, these nodes can actually be sorted into communities or subnetworks. And these community of brain regions have strong connectivity with each other, but form weak connectivity with the brain regions that are outside of the community. And these communities may form the basis for specialized subunits of information processing. So on the second level, on the mesoscale, we could also study these networks from the perspective of communities. And finally, and more traditionally, as I'm sure many of you know, that one could also study these global summary statistics for the entire, to capture the information for the entire network, such as the global efficiency or the characteristic path lines at the macro scale. So indeed, using the features from any of these three scales, the network neuroscience community has studied a diverse range of questions, such as development, the sex differences, cognitive functions, health versus disease, and motion artifact. But most commonly, these studied, they investigate the brain networks at one scale at a time. So for example, you could imagine that you could build a statistical model on every single individual edge. And this process would first involve an initial vectorization of the connectivity matrix, which means basically we would have to flatten a symmetrical matrix for the adjacency matrix for the brain connectivity, which often comes with these prominent block structures, into a structureless feature table. And of course, these have, building a statistical test for every single edge for a graph usually comes with tens of thousands of edges, comes obvious pros and cons, like Stephanie for the first presentation very nicely demonstrated. So the pros, of course, that if you build a statistical model for every single edge, you would capture lots of information. But the con is also obvious, that it ignores those block structures that I showed you earlier, and you have to do a massive correction for the really high number of multiple comparisons. And in the process, you might have to end up inflating the type 2 error. And of course, even some of the results turned out to be significant at the end after applying the correction. The results for every single edge might also still be difficult to interpret. So alternatively, given the ease of interpretability, one could also study the within and between community connectivity. So while the results would be readily interpretable, because then you can make inferences on the within and between community, it certainly risks mixing a large amount of information when summarizing these really big communities to just one number. And you are certainly at the risk of kind of mixing lots of disparate signals. So together, as you can see, while it is easy to implement the single-scale approach to study these brain network phenotype relationships, one fails to model the richness of information that may be present on other scales. So in we are, it'd be great if we can develop a network regression method that one captures as much useful information as possible, like the edge-based model would, but at the same time that achieves a balance between the type 1 and type 2 error. And finally, the results you end up at the end would be nice to easy to interpret. So in collaboration with some of the most fabulous statisticians across the US, including Daniel Whitten at University of Washington, and some homegrown talents at Penn, such as Taki Shinohara and Zomi Ma, we developed a network regression method that one captures both the edge information as well as information from the community scale. So how does that actually work? And we conveniently named it the multi-scale network regression. So briefly, in this model, the goal here, again, is to predict the connectivity matrix. Here we denoted as the adjacency matrix. That's why it's A for the I subject. And first, we would have the theta term, which represents the edge-level mean connectivity matrix across the subjects. And then we have the variables of interest that you would like to extract, bring phenotype relationships for. For example, age, cognitive performance, or clinical symptoms. And then critically, we have this gamma term here, which represents the community level associations between the variables of interest and the connectivity. And the W here denotes the community assignment for each node, which is determined a priori. So you can pick your favorite community detection algorithm to come up with the node assignment, the W. And finally, we have the noise term. So importantly, as you probably have already noticed in the graph representation for the equation, now here we're making two very important assumptions. One is that the mean connectivity matrix theta, I don't know if you can see the cursor, the theta has a low rank structure. In other words, instead of representing the mean connectivity matrix as a full matrix, right, so 200 nodes by 200 nodes, for example, we can actually use the first few principal components to represent the entire average matrix, which would explain the vast majority of this variance. And the second assumption here that we're making is that the community level relationships, basically it's saying that if one edge that belongs to the same community, then their relationship, their coefficient between the connectivity and the variable of interest would be the same. And this level of relationship is sparse. In other words, some of the coefficients you can see here between the covariates and the connectivity are exactly 0. And the tuning parameters lambda 1 and lambda 2 control the level of rankness and sparsity respectively. So we empirically tested this new method using the Philadelphia neurodevelopmental cohort, which is a large single-site neuroimaging data set with over 1,600 subjects. And first, we set out about 20% of the data as the left-out validation, which we will use to test the generalizability of our model. And in the remaining 80%, as you can see from the blue bars, we performed a 5-fold cross-validation to select the tuning parameters for the rankness and the sparsity. So here, through an iterative process and the 5-fold cross-validation, we obtained the optimal lambda 1 and lambda 2, which again, they control how much rankness the mean connecting matrix theta has and how sparse the community level brain phenotype relationship matrix gamma is. And this tuning process has kind of revealed a smooth convex objective landscape without very obvious boundary effects, which is just a fancy way of saying that we're pretty confident that this particular combination of lambda 1 and lambda 2 here gave us the best prediction performance, but just in the training data. So we still have to evaluate our model after we have determined what the optimal lambda 1, lambda 2 is. And in order to evaluate our model, we first tested in the validation set, which we set aside at the beginning, the 20%. And you can see that it yielded comparable prediction error here as in the training and testing. And secondly, to test further the statistical significance of the model, we permuted the data such that the variables of interest are assigned to somebody else's brain networks. So we did this for 1,000 times, and in each time, we built a new model using the permuted random data. And as you can see here, and then we use the permuted model to predict the adjacency matrix in the validation set. As you can see here, the distribution of 1,000 permuted models, none of them was able to beat the model built with the real data. So what did the MSNR, the multi-scale network regression, really find in the PNC? So in regards to age on your left side, we counted how many within and between community edges increased or decreased with age. And indeed, we found that more within than between community edges increased with age, and more between than within community edges decreased with age. And if you're familiar with the developmental literature, you will see that this finding is actually consistent with prior results of basically there's a network segregation in the normative process of network reconfiguration during development. And on your right side, we also recapitulated the known effect of distance-dependent motion effects on estimation of functional connectivity. So specifically, if two brain regions are closer together, higher motion would actually cause their apparent functional connectivity to increase, whereas if two brain regions are farther apart, then higher motion would actually cause their functional connectivity estimated to decrease. So finally here, we also conducted head-to-head comparison of MSNR and the common single-scale approaches that I mentioned at the beginning. So specifically, we examined the level of prediction performance and the interpretability of each method. So in short here, you can see that MSNR did well in both the out-of-sample prediction and the interpretability, whereas the edge-based models, they sacrifice the interpretability by having basically tens of thousands of parameters in order to have a similar prediction error as the MSNR. And in contrast, the community-based models, they exhibit a high level of interpretability similar to the MSNR. However, this was done at the expense of poor prediction error for the community-based approach. So in summary, we developed a panelized multivariate regression method that models connective networks from a multi-scale perspective. And the MSNR recapitulated known brain phenotype relationships in a large neuroimaging data set. And compared to some of the common single-scale approaches, MSNR achieved a balance in the trade-off between prediction performance and interpretability. Of course, there are very obvious limitations as well to this method since it's still, version 0.1. So there's, in fact, even though I call it a multi-scale network regression, there's certainly more than one definition of scale, and these at least would include the topological, temporal, and spatial scales. And here in this method, I'm specifically referring to the topological scale, but there could also certainly be a lot of interest in developing multi-scale network that really include other kind of types of scales of the network. And finally, the permutation test was run from the entire model, so we couldn't actually make any inference on the association between the brain networks for any individual variables of interest, and that could also be an extension to being worked on for further study. So either way, we hope that the approaches such as this could have the potential to yield novel insights into brain behavior relationships that incorporate more realistic multi-scale network architecture. So with that, I would like to thank my mentor, Theodore Satterthwaite. I hope you finally make into this room, and for everybody for your attention. Thank you.